So for the simulated MIRI data, we provide the level 0 raw data for all of the 6 MIRI pointings, just introduced by Steve. And the simulation was done by MIRISim, the software dedicated for MIRI simulations. And the input sources are also from the SAM catalog, and we also include a few the real-life redshift of 9 candidates, because we want to test the MIRI ability in detecting and studying those really interested sources. And for the data format looks like this. For each of the pointing, there might be several filters, and which indicated by the filter ID here. And also for each of the filter, there might be multiple deezers, and which indicated by the deezer ID. And here is an example of the file name, and so we have many of those files for the raw images. So for the pipeline, we have our customized pipeline in the Jupyter Notebook format, IPYNB format. So on the right-hand side, you can see what it looks like. I will show step-by-step later and how you can run this pipeline, but this is how it looks like. So the input for the pipeline reduction is just our simulated raw MIRI data, and the output is a fully reduced mosaic image as well as the width maps. And you can play with those fully reduced mosaics with your source detection algorithm, your photometry, and test your algorithm, your tools, and ready for the real JWST data. And we also provide an optional source detection and photometry using photoutils. But this is just for demonstration only because we just don't fine-tune the photoutils tools that we use here. Yeah, but the photoutils, of course, is not necessary. You can also use other advanced tools such as source extractor and T-Photo for example, for PSF match photometry. So here we just want to show you how to, when you have the photometry catalog ready, how you want to compare with the model photometry and see if you achieve the 5 sigma depths, for example. And here is what it looks like for our pipeline reduced image. And the central 2 panels, the maps are for the false color MIRI images as indicated by the text here. On the left is the Hubble image. On the right is the MIPS image for comparison. And there are also 4 zoom-in panels. And if you look at the zoom-in panel, you will see that we can really capture the MIRI mid-infrared colors with our really high-resolution MIRI image. Also, the sharp image is very amazing. It's quite comparable to Hubble. So that's good. So we can have a sense of what the galaxy looks like in the mid-infrared band. But in the MIPS, you can see we can do nothing, everything is point-like sources. But the high resolution also brings you sometimes some troubles because you cannot take the source as point-like sources. So when doing photometry, you need to consider the source shapes. You need to adjust your aperture properly so it gets the maximum signal noise, and it also gets the most of the flux. But in the MIPS, things are easier because everything is point-like sources. So you just do an aperture photometry and do a well-defined photometric correction. In the MIRI, we will see you will need to be more careful about the photometry. How to run a pipeline on your own machines? Of course, today we just, for simplicity, we just use a pipeline on the Space Telescope servers. But later you might want to download to your own machine and to play with it because the server is not permanent. It might change and it might work for the future. And I highly recommend to download the pipeline to your own machine. You can download it using our CEERS website, which have all the data release. And of course, there needs some dependencies for the pipeline. I think you will need a Python version above 3.8. 3.7 might also work, but 3.8 is highly recommended because it's also compatible with the calibration pipeline. And you will, of course, we also need the Jupyter notebook to open our IPYNB file. And for now, I think the Linux and the Mac are supported, and those have all been tested. But I have not tested using Windows. I guess there will be some compatible issues with Windows. I guess it's not a problem because for most of us, we all have Linux or Mac. And there are also some dependencies that are needed. Besides the common dependency like NumPy, AstroPy, we also need the JWST calibration pipeline. And for me, I have tested a few versions of the pipeline. I think our code does not depend on a specific version of the pipeline. But if you find there is a compatibility issue with your version of pipeline, just your own version of calibration pipeline, just email me, let me know. Besides pipeline, we also need AstroScripy for the cosmic ray rejection. Also, another is the SCP, which performs source extractor like background modeling that we need. And all the dependencies are in the README file. There is also the website where to download and install those dependencies. We will see later. There is a well-described README file. And you will also need quite a big disk space, 65 gigabytes. I think which is not a problem for the modern computers. If you want to run all the pointings, it will need 65 gigabytes. For the memory, I don't think there is specific requirements. I have run the pipeline using a 64 gigabytes computer, which is my desktop. I have never run into a problem. I also tried a few pointings on my laptop, which is just a 16 gigabytes, which also doesn't seem to be a problem, but although I don't try all the pointings. So I guess the memory requirement, the RAM requirement is relatively small because the data volume is small compared to the NIRCam one. So we have our customized pipeline. So the natural question is, why don't we use the default pipeline? As there are several reasons for it. The first reason is that default pipeline corrects for some effects. For example, reference pixel correction and astrometry correction. Those effects are not simulated by the MIRI sim. If we just use the default pipeline, which have those corrections, those will mess up the final products. So we need to disable those functions to avoid the mess up. The other reason is that the default pipeline assumes a constant background, and which is not true, at least for the simulated data. But honestly, I don't know whether the background will be spatially dependent or not for the real data. But at least of the MIRI sim output, raw data, we really need the spatial dependent background subtraction. And we have modeled the background spatial dependent background using the SCP package. The third reason for why we need to modify pipeline is that the MIRI sim data only have relative coordinates. That means that the image center is just a right ascension declination above 0. Everything about position is relative. So we need to correct for this. We need to add a real coordinate system properly in some steps during the pipeline running. And finally, there are several macro improvements. This include additional cosmic ray rejection using AstroScripy, also bad pixel masking, which we found that might be missed by the original pipeline, and etc. So to see one reason why we need the background subtraction, here is an example. Left is the background subtraction before our modeling, just using a default pipeline. You can see there is on the upper part of the image, the background is brighter, but on the lower it's darker. On the right-hand side is after our modeling of the background subtraction, and the field becomes flat, and there are no apparent residuals of the background, so just random fluctuations. So I think this convinces you why we need the SCP background subtraction, which is spatially dependent. At first you might found there are overwhelmingly a lot of things to learn about the pipeline. Things might be quite complicated, but no worries, we are here to help. I strongly recommend you to subscribe to our email list, which is also on the CEERS website, because we will have our future data and code, pipeline code release in the mail list. I also recommend you to read our paper if you are interested in the simulation and the data reduction details with the MIRI pipeline and the MIRI sim simulated data. So most of those are well described in our paper. And finally, if you have more information, more questions after the JWebbinar, you can contact my email, which is here.